Good morning and welcome to Purdue University and the Computer Security Seminar. Our speaker this morning is Mohamed Shehab from Electrical and Computer Engineering here at Purdue. He's a PhD student, and his topic today is watermarking relational databases.
Hello, good morning. So I'm going to talk about watermarking is well known in a lot of areas where there is audio, video, and other types of media. Today I'm going to talk about a special type of media, which is relational databases. So the outline of my talk, I'm going to start with some introductory material, telling you about what is watermarking and why watermarking and how watermarking can be done. And then I will talk about the general watermarking model. Then we will discuss one of the watermarking techniques. Actually, it's the first watermarking technique introduced by Rakesh Agrawal. And then we'll talk about another one introduced by someone in Purdue, Radu Sion and his group, Mike Atalla, and sorry to miss the last one. And then the future challenges and the references used in this talk. Okay. So what is watermarking? So a watermark is a signal. In our case, it's a stream of bits. It's a signal that is securely and imperceptibly and robustly embedded into the original content, producing a watermarked signal. So why did I highlight robustly here? Because there are two types of watermarks. There is a watermark which is robust, and there is a watermark which is fragile. And according to the application, we would like to design a robust watermark or a fragile watermark. So what does the watermark describe? It describes information that can be used for proof of ownership or tamper-proofing. So tamper-proofing is like integrity checks on the data, while proof of ownership is that if you design a document, you want to prove one day that you are the owner of this document. So watermarking can be divided into two types, a robust watermark and a fragile watermark. So a robust watermark is a watermark used for proof of ownership and copyright protection. So by robust, I mean that the watermark, the attacker will have a very hard time trying to remove the watermark from the data because the watermark is robust. And what makes it robust is the technique that we will be using to embed the watermark. The other type of watermark is fragile watermark. A fragile watermark is a watermark which certain changes to the data will disturb the watermark. So this disturbance of the watermark will tell you, hey, this data has been altered. Okay, so that's why it's fragile. So in fragile, we will be using it for tamper-proofing and data integrity. So in this talk, I will focus on the robust side of watermarking. Not a lot of research has been done in the fragile part, even in media, because it's very hard to design a watermark which you can retrieve and changes. So there is two contradicting assumptions here, that the watermark will change and you can retrieve it. So that's what makes fragile very hard. But robust is you are trying to hide the watermark in very secret places where even the attacker cannot reach to these places. Okay? So why watermarking? So watermarking is done because digital media can be easily distributed now, copied through the web. And database outsourcing is a very common practice. Database outsourcing, what type of data? For example, stock market data is being outsourced, consumer behavior data. We have a big database here at Purdue by Walmart. And the power consumption data also at Purdue, we have power consumption data. And the weather data. So all of this is being outsourced continually. So watermark provides a very effective way of proving ownership. Why? Because if you embed a watermark in the signal, this means the signature information is inside the signal itself. I mean, it's inside the document. So you don't have a document and a signature. No, the signature is embedded in the document. So they are all acting as one object. So signature and data are the same object. And it also devises an effective means for tamper-proofing. The integrity information is also embedded in the watermark, in the data. So why is watermarking possible? And if I'm going to embed something in the data, this means I will have to change the data, right? So if I will have to change the data, this means this data should tolerate the change that I'm going to make. So real-world data sets can tolerate a small amount of errors without degrading their usability. The magic word is usability here. Okay, so usability, I have the next slide will talk about usability, but let's see, for example, some examples. The meteorological data in building weather prediction models, the wind vector and temperature accuracies in this data can be estimated within 1.8 meters per second and 0.5 degrees Celsius. So this is the amount of error that happened when you measure this data. So this amount of error gives you a usability region, which you can play with and alter the data in that region. So you can play with, for example, the wind speed with a percentage of 1.8 plus or minus. Okay, and then so these constraints will bound the amount of change that you can do on the data. Simple. Of course, I will not be changing the data haphazardly. No, I will have constraints that I have to abide by. So what defines the usability constraints? So the usability constraints are application dependent, obviously. So why are they application dependent? For example, alterations performed by watermark embedding should be unidentifiable by the human visual system, for example, in images and video. So if I have an image and I embed a watermark in the image, the images before and after watermarking will have to look the same for to the human eye. Okay, that's application dependent. For example, consumer behavior data, watermarking should preserve periodicity properties in the data. So consumer behavior meaning that every day you go buy, for example, milk from Walmart. Okay, so there is a periodicity. Every day people buy milk from Walmart. If I'm gonna embed a watermark in this data should still give me the same periodicity that every day people buy milk from Walmart. Okay, at certain periods of time, whatever. Actually, I was surfing the web today, and I thought maybe I should bring this just as a small example. So, for example, Google has provided a new service called maps.google.com. Maybe you can try it out. And if you look closely here, you'll find that Google embedded watermarks. But these are visible watermarks. You can see them, right? Why did they embed the watermarks? They want to prove ownership on this data. Did this watermark affect the usability? Yes. But did it affect it large enough? No. I can still, this is of Chicago, actually. I can still define the main regions of the picture while the watermark is still there. So usability is application dependent. Okay, what are the properties of the watermark that I would like to have, or that we would like to have in our design? Detectability. And this detectability meaning that the detectability is based on a secret key. So I can easily detect, the watermark can be easily detected only with the knowledge of the secret key. Okay? Robustness. The watermark cannot be easily destroyed by modifying the watermark data. Imperceptibility, meaning that looking at the data, you cannot find the watermark. Yani the watermark is imperceptible. Presence of the watermark is unnoticeable. And a blind system. A blind system means that to detect the watermark, you don't need the knowledge of the original data. You only need the watermark data and the key, of course. So you do not, because if you see, if I have the knowledge of the original data, the problem becomes very easy. All what I do is just subtract both of them, and then what is remaining is the watermark, plus the attack produced by, plus the effects of the attack, plus the effects of the attacker, right? So that's why we emphasize the blind system. Makes the design a little bit harder. Okay, so what did we talk about until now? We introduced watermarking, and we motivated the problem a little bit. The next section, we will talk about the general model of watermarking. So here is the general model. We have our data. You can see the pointer, right? Okay. We have our data, and we have 3 blocks. The first block is the watermark encoder. And providing a secret key, the data, and the watermark is generated. The watermarked version of the data is generated. And then it is being exported to so who performs this? It's the owner of the data. He watermarks his data. Then he ships the data to a client. So when it's being shipped to the client, an attacker can attack this data. We will discuss what types of attacks that he can perform on this data. And then the attacked version is with the client, or the attacked version is being sold to someone else. Hey, this is my image, but it's not yours, and you are selling it. So how to prove ownership? All what we require is the secret key and the watermarked version of the data. And using the secret key and the watermarked version of the data, we should be able to decode the watermark that is embedded. Okay? Very simple model. Okay, so how is relational media different from multimedia? So multimedia objects consist of a large number of bits with considerable redundancy. Actually, this is what makes MPEG 7 and MPEG fly, because there is a lot of redundancy in this data. As there is a lot of redundancy, there is a lot of space to hide things. But in relational databases, all what you have is just a list of numbers independent of each other most of the time, and there isn't that much of bandwidth to hide data in. And the relative spatial and temporal positioning of various pieces of the multimedia object typically does not change. For example, you remember the picture I showed you of Chicago? There is a lot of blue region. So I can hide things in the blue regions without affecting it. That's why even MPEG works, because there is a lot of pixels that are related. But in relational databases, no. The tuples of a relation, on the other hand, constitute of a set that is not that there is no implied ordering between them. Like that's an assumption. Then portions of the multimedia object cannot be dropped or replaced arbitrarily. I cannot remove navy pier and put something else there, from the Chicago picture. Someone will look at the picture and say, hey, this picture is fake. But in relational data, no, you can remove, like for example, if I have the list of your ages, for example, I can put in more tuples, or I can remove tuples, and the data is still valid. So what is the attacker model? So we assume that the attacker has access only to the watermark data. Only the watermark data set. Okay? The attacker's goal is to weaken or even erase the embedded watermark. At the same time, keep the data usable. Of course, I can easily destroy any data set. Like this picture of Google, I can just go and keep erasing everywhere. I'm destroying the picture. But I'm also destroying the watermark. But the picture is not usable. Right? So there is a dilemma here. By how much he will change the data such that he will erase the watermark and not destroy the data. Okay. So what are the possible attacks in a relational database? You can delete tuples. You can alter tuples. Or you can insert new tuples. So we have talked about two sections, the introductory material and the general watermarking model. Now we will go ahead and talk about one of the techniques used in watermarking, and it is the first proposed watermarking technique for relational databases. So what are the main points of this technique? They are going to watermark numerical data. The technique is dependent on a secret key. Works, so it's until now working with our model, right? You need a secret key. Uses markers to locate tuples to hide watermark bits. So you see, you have a list of tuples. And you're trying to embed something in these lists of tuples. So you have to mark which tuples you want to hide things in. So it uses something called markers that we will discuss now. How are these markers being discovered? And hides the watermark bits in the least significant bits of the data. So we are dealing with numbers, and numbers have least significant bits. They are going to hide data in the least significant bits. Actually, hiding watermarks in the least significant bits is the oldest form of data hiding. People have found that least significant bits do not change the usability much of the data. For example, but this is an assumption also. Flipping the least significant bit from 1 to 0 will not have much effect on the data. This is the assumption built that is used to design this technique. So let's talk about the encoder version. So the encoder version, they do not provide technique to enable the user to provide his own watermark. Instead, the watermark is a function of the data and the secret key. That's a limitation in this technique. So what they're going to do is the watermark is not like arbitrarily chosen. No, it is based on the data and the secret key, and we will see how. So now let's talk about the assumptions that the encoder will have. The encoder assumptions. They choose 4 integers, which are K, E, M, and V, are randomly selected by the data owner and are kept secret. Okay? K is the secret key. E is the least significant bits that can be altered in a number without affecting its usability. For example, you define E. You say E is 3. This means that this is C, this is your binary number, and E is 3. This means you can alter the last 3 bits. Okay, it is a user-defined variable. Okay, M is used for marker selection. We will see how. It's an integer. Okay, it's used for marker selection. V is the number of attributes. See, a relation is tuples, right? A relation is tuples. This is the horizontal description, and the vertical description is attributes, right? So the number of attributes that will be used in watermarking is decided upon by V. V decides the number of attributes that will be involved in watermarking. Okay, so now let's see the encoder algorithm. So for all tuples in D, D is your database or your relation. Okay, for all tuples in D, R is used to define the tuple. Anything in red is secret, just for your convenience. Okay, So r.mac, R is a tuple, right? R.mac is message authentication code. MAC is message authentication code. Message authentication code is computed as follows. It's the hash. Hash is a secret hash. It's a secure hash. It's a one-way function. It's like SHA-1 or MD5, right? So it's the secure hash of the key concatenated. These pipes are concatenations. Concatenated with R.P. R.P is the primary key. You know, in any relation, you have a primary key, and then you have some data, right? So this is the primary key of the tuple. And concatenated with K. So this is how the MAC is being computed. So the MAC is a function of the secret key and a function of the primary key. Make sense? Okay. So this is computed for each tuple. Yes, go ahead.
Why is that K concatenated?
Yeah, this is for secrecy. Because if I just compute it based on the primary key.
Why not just one K?
Oh yeah, they proved that if you concatenate both Ks, it's secure. Yeah, that's not from my side. So they proved that it's secure if you concatenate, if you use this form. Okay? Make sense? So now I have computed a MAC for each one of the tuples. Now I need to select the tuples that I will hide data in. And it is very simple. What they do is, for each MAC, they compute the modulo with respect to M. M is defined by the user. And if this modulo is equal to 0, this means it's a marker. This means that, hey, this is where I'm going to store a bit. How will I store the bit? I will hide it in the least significant bit. But I have E bits. Okay? See, now what did I select? I selected the tuple, right? This marker will select my tuple. I actually have a diagram after that explaining it very well. But I selected the tuple, then I have V attributes. Which one of the V attributes will I use? So, the attribute ID is also the MAC modulo V. V is the number of attributes. So this will give me, this will triangulate on one attribute now, right? Tuple attribute, it's a point. Now you have a number. This number has E least significant bits. Which one of the E least significant bits? The story completes. I also do modulo E. Okay, this gives me which bit I will be changing. Now what do I have to do? Change the bit, right? But how to change it? It's also decided on the MAC. If the MAC is even, modulo 2 is to define if it's even or not. If it's even, set the bit that you selected. If it's odd, clear that bit. Simple. So what I'm trying to tell you here is the relation. I compute the MAC, modulo M, for each one of the relation. Remember, the MAC is computed as the secret key, concatenated with R.P. R.P is this. Is the primary key of the relation. Make sense? So I'm computing the MAC and computing it modulo M. So the one which is 0 is the one I'm looking for. So here it is. So here is the first selection. I selected the attribute. Sorry, I selected the tuple. Then I have to select the attribute. So here is the attribute selection. The attribute selection is based on MAC modulo V. I have the attribute. So now I know there is a value sitting here. Okay, here is my value. Which bit I'm going to change? It's decided on MAC modulo E. So I have the bit here. Then according to if the MAC itself is even, I will clear the bit. If the MAC is odd, I will set the bit. Make sense? Actually, very simple technique. So now let's talk about the decoder. How will I decode this? So let's just go back. Decoding means I will try I have embedded the watermark. Now I would like to derive the watermark out. Decode it. It's very simple, right? It will have to be the opposite, right? Or you have to go the same path to reach to the same bits, extract the bits according to the same idea. So here we define two variables. One of them is the match. Match meaning that if the bits match, we will increment match. Match is the number of bits that match. Match. You remember you have embedded a watermark, and there is a watermark that you are going to extract. The match will describe the similarity between them. Okay. While the count is the number of bits that you have decoded. Okay. So match will signify the number of correct bits decoded. The total count is the number of bits decoded. Let me repeat. I see a lot of faces wondering. So match is the number of correct bits that you have decoded. The total count is the number of bits that you have decoded. Right? So correct and total. Okay. So now what do? We have to go through the same process, right? So for each tuple, given the set D, for each tuple you compute the MAC. And then if the MAC is equal to 0, modulo M is equal to 0, you go this. So this means you have decoded 1. That's why we increment the total count. And then you select the attribute, you select the bit. And then accordingly, if the bit is set, say if the MAC was even and the bit is set, you increment match. Otherwise, you check also if it was cleared, and you increment the match. Make sense? Okay. So here I'm just doing the same exact technique, but other than embedding, I am detecting. Make sense? Okay. So now there is what does this technique do? They define a threshold. You know, you have the number of correct bits and the total number of bits. You divide them by each other, gives you the percentage correctness, right? And the percentage correctness has to be above a certain threshold. If it's above a certain threshold, this says, hey, the watermark is present. If not, the watermark is not present. How is the threshold decided upon? It's also application dependent. Like if you have a very critical data, you would like to have it in like the upper 90%, this threshold, right? Or if the data, yeah, it depends on the application. The decoder, same story. You compute the MAC, you locate the tuple, locate the attribute, locate the data, look at the bit, and decide if it's correct or no. So what are the strengths of this technique? So, okay, what are the strengths of this technique? One, it's computationally efficient. Big O of n. All what you have to do, big O of n means it will run in linear time. Meaning that n is the size of the database, okay, or size of the relation. All what you need to do is examine each tuple. So you are just going to touch each tuple, and it's big O of n. No complicated. No tuple sorting is required. You just go over the tuples, and according to the primary key and the MAC, you can decide on it's going to be selected or no. It also has a property called incremental updatability. Means that if you have a relation and you have already watermarked it, and then you add alpha tuples to this relation, the alpha tuples can be independently watermarked from the previous relation, because all what you need to do is for each tuple test its primary key and see if it's a marker or no. If it's a marker, you watermark it. If not, you just leave it. Make sense? What are the problems of this algorithm? So one is we have seen from the first slide in the model that it does not provide a multi-bit watermark. All the operations are dependent only on the secret key. Remember, I crossed the watermark. Remember that? That's why did I cross the watermark? Because this technique, the watermark is decided based upon the primary key, remember, and the secret key. That's how my MAC is being evaluated. It's not resilient to alteration attacks. Alteration attacks means attacks that will alter the data. Least significant bit, LSB means least significant bit. Least significant bit can be easily manipulated by simple numerical alterations. Very simple. If you take the least significant bits and shift them one position to the right, you messed up the bit. Because your watermark bit is one of these bits. And if you move it, there is a probability that this bit is going to be erased. Or if you clear all the bits, or set all the bits, or flip all the bits, these will not affect the usability much, but they are going to erase the watermark. So watermark erasure is very easy in least significant bits. Then this requires the presence of a primary key in the watermarked relation. Like you need a primary key as one of the attributes. And this means, actually, usually the primary key is just an arbitrarily chosen index. So someone can erase all the primary keys and put his own primary keys. Just satisfying uniqueness, the relation is still valid. So that's a weakness in this technique. Also, this technique does not handle usability constraints, complicated usability, other usability constraints. For example, category preserving usability constraints. Let me tell you about that. For example, the age data. Someone age 20, this means he cannot drink, right? If you insert a 1 in the least significant bit, 20 becomes 21, and he can drink now. So now the category has changed. So least significant bit embedding does not take care of this. Make sense? Okay. So go ahead.
Is there anything that would keep a second watermark from going? Someone else comes along, grabs this image or whatever, embeds their own watermark with the same technique.
Yes, I have a slide for this. Okay, let's wait till the end. I prepared that slide today morning. I have that slide. Yeah. What his question is, what if I embed a watermark in some picture or some data, and I give you that data, and then you embed your watermark, and then you go to court and say, hey, this data belongs to me, and then the court uses your key, they find your watermark there. How can we resolve this issue? It's a very complicated issue, but I have a slide for this. So the next technique is by Radu Sion, Professor Mike Atalla, and and Professor Sunil. Okay, so now technique number 2, these are the points. What are these points? Yeah, these are the highlights. What's being used in this technique? For example, 1, also we are going to deal with numerical data. 2, the technique is dependent on a secret key. So we are abiding by the watermarking model. Instead of the primary key, the tuple primary key, it uses, or the relation primary key, it uses the most significant bits of the normalized data set. We will see what normalized means in one of the slides. So it has a solution. It doesn't use the primary key. Divides the data set into partitions using markers. So you remember the first technique, markers decided where you are hiding the data, right? You are hiding the bit. Here, they will hide the data not in one tuple, they will hide it in groups of tuples. So to decide where are the groups, you partition the data using the markers. We will see how. Varies the partition. So instead of embedding in the least significant bits, it will insert the least significant. It will insert the watermark bits in the statistics of the numbers. We will see how. So this is the general model. It abides by the general model, and let's talk about the encoder. So before we talk about the encoder, I want to discuss with you how to hide a single bit in a number set. You have a number set, and you want to hide a single bit in it. If we can solve this problem, we can easily embed a single bit in the partitions that we devise. So for example, what's the problem? Given a number set Si, which is S1, S2, blah, 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 to Sn, how to vary their statistics to embed bit Bi, subject to the provided usability constraints. So there will be usability constraints, and you want to embed that bit in this number set. We will see how. So this is the set Si. It's just a list of numbers. I am putting them on the x-axis. Okay. Then I define mu as being the mean of these numbers. So this is mu, the average of these numbers. Sigma is the standard deviation of these numbers. C here in this relationship is a constant decided upon by the user. Now if I do mu plus C sigma, I refer to this as reference. So this reference is sitting somewhere here. And you see this is C, standard deviation. This is the... I'm not doing rocket science. It's very simple. This is the reference. The reference is decided upon the mu, which is the average, and C places from the standard deviation. C standard deviations. So I have a reference. So I have now a point. The number of points on the right of the reference is referred to as positive violators. And these are very interesting the number of points. So here, for example, I have 6 points. This means the positive violators are 6. Okay? Where am I going to hide the watermark? I will hide it in the number in this number, in here. Let's see how. So here is my set. What we do is, the number of points on the right of the reference, what is the range? Yani by how much they can vary. They can be 0. They can be 0 points here. Or there can be all the points here. Yani these are the worst case. Of course, there can be bounds that are tighter than this. So, So, on this side, I can have 0 points. Or I can have, at most, the cardinality of S, which is the number of points. Right? Okay. Now, the user decides upon V false and V true. These are user decided constants. V false and V true, and they are fractions. Okay? Now, if I want to hide a 1 in here, this means I would like to change the number of points here to map into into this region. Oh, so let's assume I want to embed a 0. I want to embed a 0. This means I would like to change the number of points here such that they map to a number here. Like for example, if this is 5, you see the pointer, right? If this is 5, and I start up with these number of points here, 10, I would like to reduce them to be less than 5. So I will be varying the data such that I am playing with the number of points here. This is if I want to embed a 0. If I want to embed a 1, I would like to change the number of points here to map in this region. Very simple, actually. You know, they are only playing with the number of points here. But what complicates this problem is your reference is not constant. What is the reference again? The reference is a function of the mean, which is the average of the numbers, and the standard deviation of the numbers. So if you are going to embed, to increase the number of points here or decrease them, this means you are going to move some points. Say we want to increase them. This means that I'm going to move some points across the border, right? Across the reference. But as you are moving points across the reference is also moving. So that problem is not that trivial. So in Radu's paper, or in this paper, when they discuss how they are going to manipulate the number set, it's not very clear. What they do is they choose the number of points, the points which are closest to the reference, and they try to move them across the reference, either from the right to the left or from the left to the right. But the main idea is you are trying to change the number of points on the right of the reference, either increasing them or decreasing. Okay. So how to avoid using the primary key? So what did I show you here? I showed you a technique. If you have a list of numbers, I can hide in this list of numbers a 1 or a 0. Okay? Yes?
Where are the user constraints?
Yeah, I will show you. Yeah, the user constraints are enforced when you are changing the points.
Okay.
Yeah, so when you are changing the points, the user constraints will constrain the amount of movement for each point. So, for example, if you try to move this point from here to here, the user constraints may not allow you, right? So the user feasibility constraints, they devise a feasible region of all the points where they can move, right? Such that the usability is not affected yet. Yes. Yeah, good question. So how to avoid using the primary key? They have a very ad hoc solution. The ad hoc solution is, given a number set Si, generate the normalized Si. How? What do they do is, the normalized is, you get Si and divide it by the maximum of Si. This division means that each item of Si is going to be divided by the maximum of Si. So now this maps the numbers to a region from 0 to 1. So now the numbers are normalized. And then what do they do is, for each number Sk, okay, this is not in. For each number Sk in the normalized set, use the first n most significant bits as the primary key. So they use the most significant bits of the number as the primary key. The good thing about this is that the most significant bits are not going to change after you alter your data. And the probability of them changing is very low, right? That's number one. That's the advantage. The disadvantage is, now the user, from the numbers, the user can have an idea where are you hiding things. Because he now knows that you are using the most significant bits, and he can devise statistics to find what numbers group with what numbers, and then what numbers are in the same partition. Let's see. So now let's talk about the decoder. When I say r.p, I mean the primary key, which can be either a primary key in the relationship, or it can be the primary key derived using the most significant bits. Okay? So now, the first step is to compute the MAC for each tuple. We have done this before, right? So for each step, we derive the... Yeah, another assumption here is that the relations are a single attribute relations. This means you don't have multiple attributes. You only have one column. Actually, you can have two. One as a primary key and one as the numbers themselves. Or if you don't have a primary key, it will be only one column. Okay? So after you generate the MAC for each tuple, you sort the tuples according to the MAC. Make sense? So we sort the tuples according to the MAC in ascending order. So now we have the tuples sorted according to the MAC. Now I have the numbers are sorted, right? Now I have to split them into partitions. And each partition is a number set. And each number set will handle one bit. Okay, so what do we do? How to locate the partitions? So you have max, 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 max. So what you do is you locate the max that result in a 0 when the modulo is taken. So r.mac equals 0 says that this is a marker. And the data between two markers, tuples between two markers, are referred to as partitions. So tuples between two markers are in the same partition. So the first step, we sort. The second step, we partition based on the MAC. And the last step is bit embedding. How do we embed a bit in a list of numbers? We have partitioned them. It's a list of numbers. What do? We embed using the same technique that we described 2 slides ago. Make sense? So the first step is you sort in ascending order according to the max. It's a very simple slide, but maybe it will help. Then we locate the max. We locate the markers. How do we locate the markers? Is r.max equal to 0. The yellow ones are the markers. So the values between two markers is a number set. This is a partition. And then what do? We embed a single bit in each partition. How do we do that? By varying the statistics. See? So for example, in this partition, we have embedded a 0. In this partition, we have embedded a 1, 0, 1, blah, blah, blah. How are we embedding? By varying the statistics. Let's talk about the decoder. Very symmetric. What do we do in the decoder? We sort and partition the same way, right? Because we have sorted and partitioned to find the partitions. We do the same thing. So partition the data set using the same approach used in the encoding phase. And then bit detection. What do is we look at the violating set. We compute V of C, which is the number of points to the right of the reference. And accordingly, we decide, is it a 1 or a 0, right? Another thing is, to compute the number of points to the right of the reference, what do you need to compute? You need to compute the average of the numbers, which you can compute from the numbers you have. You need to compute their standard deviation. You can also compute it from the numbers. And you know C, so you can find your reference, right? After you find your reference, you just count the number of points to the right of the reference. If the number of points to the right of the reference fall in the first region, this means that it's a 0. In the middle, it's undefined. And on the right, it's a 1. Let's see here. We will talk about the second step just in a while, but just in the next slide. But the third step is majority voting. I can have a lot of partitions. This means I can hide one bit, a certain bit, multiple times in the relation, repeatedly. This means when I'm decoding, I will be decoding this bit several times. So how will I decide which one is the correct one? So I use majority voting. Majority voting means that I will select the bit that occurs the most. Okay. So let's see here. So this is the watermark data set. This is after sorting and partitioning. And this is my region. All what I have to do is what? All what I have to do is compute the reference for each one of the partitions and then see if the number of points fall here or here. If they fall here, the bit decoded is 0. If they fall here, the bit decoded is 1. Then what do? I decode the bits. Then I map it to a map here. This map is 0 maps, this is the first bit decoded, 1 is the second bit decoded, 1 is the second bit decoded, and you see 3, and it keeps going. 0 is the third bit decoded. And if your watermark length is 5 bits, is 6 bits, this means that the 6 bits will be repeatedly embedded in the relation. So how do you decide? It's by majority voting. For example, here you have decoded 0, 0, 1. This means that zeros have occurred the most. This means the decoded watermark is 0. Make sense? So here we are introducing some redundancy. We are embedding the watermark several times. Actually, it's a very famous technique, a very old technique in communication systems, which is referred to as repetition codes. Where, hey, I'm going to send you a bit, but every time I'm going to send you this bit, I'm going to repeat it n times. And then n has to be odd, so that if the number of errors happen is n over 2, you can still decode your bit. Make sense? It's a very famous technique, actually. It's called repetition code. So that's simply what we are doing. Let's talk about now what are the problems. Let's talk about the strengths, to be fair. Okay. So the strengths, the bit embedding technique honors the usability constraints. So we can enforce the usability constraints while we are changing these numbers. And then it embeds the watermark in the data statistics, which makes the technique more resilient to alteration attacks when compared to the least significant bit technique. Just remember, the least significant bit technique is very easily attacked. But this technique, you are embedding it in the statistics. Plus, no one can find the partitions. No one will know which two numbers are in the same partitions because it's decided upon what? Decided upon the primary key and your what? Your secret key, the partitioning. Okay, okay, let me show you a type of attack that can happen here. This is my watermark data set. And this is the data that is embedded in the data set. Okay? Now let me add tuples. See, the problem of adding new tuples, what can happen? If you add tuples, you are adding more information, you can add markers. If you add markers, this means you are adding partitions. If you're adding partitions, this means you are adding a new bit to the watermark. So that's why they call it synchronization attack. So let me see, the added marker will be designated as in red. Here, see, this is the first case. This is the original watermark data set. I add a tuple. What happens is, from one partition, you go into two partitions. This partition is split into two. And assuming that the bits here is 1, that the decoded bits are 1 and 1, what happens is the following. What happens is, as you are inserting a bit, as you see here, there are 3 ones here. Now they become 4. There is a shift in the watermark. This shift is referred to as watermark synchronization error. If you decode, what happens is the ones in red are the errors. All of them are wrong. See, this is the original watermark that is embedded. See what I am decoding? So this technique is very weak for when exposed to addition attack or tuple addition attack, because you can add markers. Now let's do tuple deletion. If you can delete tuples, this means you can delete markers. This means you can delete bits. Same story. So here is the same story, but the complement. Here we are deleting markers. So here is the relation, and here are the markers in yellow. Now I will delete one marker. See this marker deleted? You can see it. Okay, the marker is deleted. What happens is one bit disappears. Now instead of shifting the watermark to the left, now the watermark will shrink. Right? You see? See here you had a 0. This disappeared from here. It become only 3 ones, and there is a synchronization error, and all the bits are decoded wrong. Make sense? So this technique is, so what are the weaknesses? The watermark suffers badly from watermark synchronization error caused by tuple deletion and tuple addition. Synchronization errors. Then there is a problem in this technique that there is no optimality criteria when choosing the decoding thresholds. The decoding thresholds are v false and v true that define where is your bit equal to 0 or bit equal to 1. These decoding thresholds are just decided upon by the user. And as one of your colleagues has mentioned, if you enforce the usability constraints while you are moving the points, you may end up not being able to move a point from a certain region to match the bit that you want to embed. So it may cause errors even in the absence of an attacker. Then there is no clear systematic approach for manipulating the data in this technique. Only a very small space of the feasible data manipulations is being investigated. So they don't formulate it they don't formulate it such that they can use all the feasible region. The technique is very simple. They only use the points that are close to the reference. Now, we have talked about the introductory material, then we discussed the watermarking general model, and then we discussed 2 techniques, one based on the least significant bit embedding, and the second one is based on embedding the watermark in the statistics of the data. Now let's talk about, we will conclude by talking about our future challenges and the references. So the challenges. So we should investigate watermarking other types of data, such as data streams. Actually, there is a paper by Radu Sion and his group discussing watermarking of data streams. But this work is very new, so only one paper that talks about this. So maybe we can investigate that. Then we should design robust watermarking techniques that are resilient to watermark synchronization errors. And then last but not least, design a fragile watermarking technique for relational databases. So most of the techniques are robust. So we would like to design a technique which is fragile. Then the references is, the first one is by Rakesh Agrawal, and it was published in VLDB. This is the least significant bits one. And the second one is Radu Sion and Professor Atallah and Professor Sunil, and it's in TKDE. Okay? And you are welcome to have any questions.
I had the one about the 2...
Oh, yeah, here it is. Okay, so what he mentioned is, the question was, what if for example, Alice and Mallory. Alice is the owner of the document. And Alice has the original document, which is D1, and then embeds a watermark W1 using Q1. Okay? So these are all owned by Mallory. And then Mallory produces D2, publicly available. Then Mallory takes D2 and then embeds another watermark in D2 using another K2 to produce a document D3. Okay, this is the question, exactly. Now, Mallory goes to court and says, hey, this document is mine. The only solution for this that I see is that if Alice provides the court with both D1 and D2, and Mallory provides provides the court with D2 and D3, the court can test D1 for using watermark 1 and watermark 2 and key 2. So if watermark 2 is present in D1, this means that Mallory owns the document, right? So it's a transitive relation. So if Alice owns D2, this means Alice's watermark should still exist in D3. That's a lot of assumptions. You know, I'm giving you a lot of assumptions now. We are assuming that the watermark W1 will survive this embedding, right? So assuming it survives the embedding, yes. D3 will contain two watermarks. It will contain the watermark of W1 and W2. And to prove that this document belongs to Alice, all what you have to do is prove that W1 exists in both D2 and D3.
Couldn't you also just say that, well, since you can generate D2 with her key in D1,
yeah,
then you can show that.
Exactly, but exactly we can do that, but here we are assuming that maybe there is some error introduced in D2 before you start embedding. So maybe that may not.
But statistically, can't you prove that?
Yeah, you can prove it. Yeah, you can. Yeah, but this is a very interesting problem that's still to be solved. You know, this is a solution as with assumptions that the data will have both watermarks. Yani this watermark will survive the second embedding, but maybe it may not. You know. So that's the problem. Any other questions? Yeah, there are 4 minutes, I think. 3 minutes.
Any questions?
Any questions? So everyone is happy with the...
Well. Thank you very much.
Welcome. Thank you.